Welcome to session 2. My name is Arnold and I will be your instructor. In this session, we will talk about risk minimization. This session is all about how to train your neural networks so that they can perform a useful task. In the previous session, we saw that the weights of a neural network determine its behavior. So the question is, if we have some actuals, both input and output, how can we determine these neural network weights? There are two questions. The first is, what is a good criterion for weight selection? Secondly, we also want to know how. How do we calculate these weights based on this criterion? These are two separate questions. The first is called risk minimization, and the second, the how to do it, is really a combination of two techniques, one called backpropagation and the other called gradient descent. Let's define our terms first. Risk is simply the average error, also known as loss, over some specific data set. In other words, a lower risk is good. The RMSE and MAE errors that we talked about in session 1 are both already averaged errors, and therefore they are a measure of risk. Risk minimization, therefore, is really just about reducing errors. We want to adjust the weights of our neurons somehow until the lowest possible errors are obtained. But the question is, does low errors on an existing data set mean a good forecast model? Well, the answer is no, because you could always have a trivial model that simply memorized the training data. It is actually crucial to prevent memorization. And this is one of the central challenges of using neural networks and other machine learning algorithms. To solve it, we will use something called the train and test trick. The idea is simply to split your data set, and each data set again consists of input and output pairs. You want to split it in time into a training data set, typically 70 to 90% of the data set, and a test data set, which is 30 to 10%. Notice that the test data set comes later in time. The weights of your neural network are only adjusted using risk from the training data set. They are not adjusted using the test data set. In other words, the model learns from the training data set but is tested using the test data set. The test data set is not used to learn. There are two phases, obviously. In the training phase, we have some training data, and these consist of the inputs X and the actual output Y. Of course, there will be many such inputs and outputs, each corresponding to a single window in time. Our neural network model is essentially a collection of weights, which are just numbers. We want to feed our model the inputs, for which we get a prediction Y hat. We then compare the predicted versus the actual output, and we use our risk function, it could be the RMSE or the MAE, to do this. And this comparison, don't forget, is not done just for one single point. It's an average error over the entire training data set. This number is logged. But this number, the risk number, or the loss number, or the error number, whatever you choose to call it, is fed into a learning algorithm. This is really the part 2, which we're going to discuss later on in this session. This learning algorithm then reaches into the model and changes its weights slightly in response to the risk that is fed to it. This cycle is called one iteration. Typically, in the training phase, we will do this again and again, and at each iteration, the model weights are changed slightly. And the promise of the learning algorithm is that it changes the weights in such a way that on the next iteration, the risk should be slightly smaller than before. What we've just described is called batch learning. And the idea is that the entire data set is fed into the model for training and the risk calculated. And the weights are only adjusted once after the entire training data set is seen. In the test phase, the test data set again consists of input and output pairs. The input is fed into the model and we get a prediction y hat. This is again compared using our risk function, and the error is simply reported. There is no adjustment of the weights during the test phase. We run the training phase several times. Each training cycle is called one iteration. After several iterations, we run the test phase once. We then observe the training and test risk over many iterations. Remember, risk for training and the risk for the test data set are different. This is a typical graph of the training and test risks. Here we call them training loss and test loss. The horizontal axis is just the iteration number. In this example, we have less than 1,200 iterations. In the first part, you can clearly see that both train and test risk decrease dramatically. Sometimes the training risk decreases dramatically while the test loss stays unchanged. But ideally, you want both to decrease. In the second stage, you see that both train and test losses decrease much more slowly. And in the final phase, you find that the training loss decreases, but the test loss begins to increase. If you recall that the model learns only during the training phase, and no learning is done on the test phase. Therefore, when the training risk decreases, this means that the model is learning to predict training actuals. When the test risk decreases, it means that the model is able to correctly predict novel data, in other words, data it has never seen before. It is able to generalize. When the test risk increases, then it is also likely to perform poorly on other novel input. Let's summarize. When both train and test risk go down, that's good. But as soon as the test starts to go up, you must stop. It means that the model is beginning to memorize the training data set. So there is a line that separates the left half of the graphs from the right half. And the line that separates it is a line after which the test loss begins to steadily increase. In the left half, the model is generalizing because both the test and training losses go down. In the second half, the model is memorizing, and this is bad. It's bad because it performs well on the training data, which it is memorizing, and this manifests itself in an increase in test losses. If the test loss increases, it means that the model is also unlikely to perform well on novel data. We can prevent memorization. A simple way is to stop training as soon as we notice test losses going up instead of going down. This mechanism is called early stopping. It simply stops training when the test loss starts to rise. Early stopping monitors changes in the test loss, and it shuts down training if the test loss starts to increase. This prevents overtraining or memorization, and it also indirectly speeds up training because you are using fewer training iterations. In this section, I'd like to explain the two techniques we use in the learning algorithm itself. And these techniques are called backpropagation and gradient descent. So the question we're trying to answer is how to perform risk minimization. In the training phase, after each iteration, the risk that is reported is fed into the learning algorithm, which in turn amends the model's weights. Let's focus on that. So this is the part that performs risk minimization, and we are just changing the weights at the end of every iteration. The technique we use to perform the minimization is called backprop with gradient descent. You can see that the risk value is simply a number, and it's a function of the predictions from the model and the actuals from the dataset. The predictions are a function of the inputs and the weights. And we know that both the inputs and the actuals are both fixed from the training or the test dataset. So let's substitute the predictions this way. Both x and y come from the training or the test dataset. In the training phase, both x and y would be from the training dataset, while w would be changed by the learning algorithm after every iteration. In other words, all things being equal, the risk depends only on the weights. So we say that the training risk is really just a function of the weights. And these are changed by the learning algorithm after every iteration. Let's see this again. So we have the training input and actual output. These are fed into the model to get the risk. We start usually with a random or a constant set of weights. We'll call this W0. Once we get our first training risk, the learning algorithm changes the model weights so that it becomes W1. So W0 initially becomes W1 after the first iteration, and this becomes W2 after the second iteration, and so on. I've used the vector W's to represent all of the model weights, not just for one neuron. This continues until we stop training. We can represent the training risk as a function of W's, and let's say it has this shape. Now this is just a schematic representation because W is a very large dimensional vector. So this will be a very large dimensional space. The idea is that we start with some W0 for which we get an initial risk R0. If we decide to change the risk towards the left and we have a new W1, you find that the risk that results is higher than R0. And so this is not good because the training risk increases. What the learning algorithm does is to change it in such a way that the resulting risk after the first iteration is lower than the original risk. Because the training risk decreases, that's good. This method of selecting the direction to move is called gradient descent. At each iteration, we find a change in W that yields the largest decrease in risk. That's gradient descent. The how of doing this is backpropagation. With backpropagation and gradient descent, we simply iterate again and again until we can't make further improvements on the risk. You can see here, once we have reached W3, any changes to the weights actually yield higher risk values. This is called the problem of local minima. If we had started near a point B, for example, then the training using gradient descent would not give us a lower minima, in this case A. Gradient descent can get stuck at local minima. Let's compare two models A and B and view their training risk as they change over time. In the previous graph, you saw the 2 points A and B. The risk for B is higher than the risk for A, and you can see that both models flatline because it is not possible for gradient descent to further improve the risk values of either one because they are both local minima. RB and RA correspond then to the asymptotes RB and RA that we observe. Solvers are a method to perform gradient descent. There are many kinds of solvers. We'll use just two in these sessions. The first is called Adam, and the second is called stochastic gradient descent. The Adam method is deterministic and it often finds good solutions, but it can get stuck in local minima. The stochastic method is fast and it works well on large data sets, but it doesn't always give a good solution. Gradient descent and backpropagation help us find the weights to use for our network. The main problem with gradient descent is that it can get stuck in local minima. The other thing we discussed was the problem of overtraining. There are two major solvers called Adam and the other stochastic gradient descent.